Welcome, everyone, to another CO2 Monday in the Refrigeration Mentor podcast. I'm your host, Trevor Matthews. And once again, like every week, I want to thank you for taking the time to come and invest with us, learn a little bit about CO2, learn about new technologies. And you're coming to see some of the greatest people on the planet that know about CO2. And I'm super excited for this conversation we're going to have today because it's a technology I do not know much about on CO2. And to me, it looks like it's going to be a huge game changer for efficiency for CO2 systems and actually simplify it. So I'm so excited to learn more about this. My guest today is the VP of CO2 for Energy Recovery, Kuo-Chiang Chen. Casey, welcome to CO2 Mondays. How you doing?
I'm doing great. Thank you, Trevor, for having me.
Well, thank you for taking the time to do this. It means a lot. It's World Refrigeration Day, one of my favorite days of the year. And I'm so glad you're here with us. Casey, why don't you give us a brief introduction of yourself and your role at Energy Recovery?
Sure, Trevor. My name is really Kuo-Chiang Chen, but that's okay. Just call me Casey. Everybody call me Casey. It's easy on me, easy on everybody. I am a VP of engineering, originally for energy recovery, and later on, after we developed this new technology, so my management want me to carry on. So now my title is VP of CO2. So, and as you can see, our ambition is not only just the CO2 for refrigeration. Later on, we believe that we can bring this one to other arenas and contribute even more to the Earth is, for example, like heating. And we believe that our PX can use on heating also.
Wow, that is super impressive. We met a couple of weeks ago at the Atmosphere America Summit, and they were going through kind of show me what it does and where it came from. Why don't we give a little brief history of where the PX G1300 came from?
Yes, sir. Trevor, this is actually a very, very good story because I personally feel appreciated about all the people who actually care about the Earth. We about three and a half years ago, we were working on, we are not working on CO2. We don't even know there's actually industry we can contribute called refrigeration. And Energy Recovery is a company that has always been in the water business. And our core business is trying to actually saving the energy for desalination through the reverse osmosis. And because that business requires a lot of energy and a lot of pressure letdown, which generate a lot of waste of electricity. And we identified this opportunity about 25 years ago. And we decided to actually come up with this device called a pressure exchanger to help to save the energy. Then at the end with this, like recently, we're pushing the efficiency of this device called a PX pressure exchanger all the way to 98.5% efficiency for water. So this is extremely, extremely efficient device to recover energy. Then about 3.5 years ago, we were approached by Department of Energy, Oak Ridge National Laboratory, and they published a paper on the refrigeration, CO2 refrigeration, and highly recommend people to look into the energy recovery devices, especially pressure exchanger. So we were of course honored. And at the same time, we were approached by DOE and saying that, why don't you guys give it a try? And we sincerely believe that it will work at helping the CO2 save energy, because that will help the adoption of the CO2 for all the commercial and also light industrial market. So we've been from the beginning, because this is the company 25 years ago, we actually invent the pressure exchanger. And then since then, we've been perfecting the technology, but always in the water side. We never thought that we can use this one for other things, because we already have actually quite a busy schedule on the water side. And then, however, the Oak Ridge National Laboratories reminder was very, very timely, because we're trying to look for other opportunities to contribute to the industry, to the Earth, and try to reduce the carbon footprint in general. So we're happily to look into that, and out of our surprise, to be perfectly honest, it's also out of my surprise. Maybe other people is not surprised, but I was surprised. This is a device originally designed for water, so saving the energy for when you pressure let down the water. But we actually proved that it can work not only in gaseous phase like CO2. You can actually work on multi-phase, like supercritical CO2, or is actually is multi-phase of a liquid and gas, or maybe even actually supercritical with gas. So all the things actually we've been trying so far is working very, very nicely. We were shocked, in fact, to be perfectly honest, and we are happily shocked, of course. And initially, we heard some naysayers saying, it's not going to work. And this is a device designed for water. Casey, don't even try. But you know what? Being an engineer, I'm a mechanical engineer by training. Then you get excited about a new opportunity. Then when people say, nah, it's not going to work, they kind of trigger your motivation, say, let's give it a try. Let's forget about CFD, model-only finite element. That we have a PX downstairs. Let's just hook it up and try it. And we try it. And that day actually marked us excitement. One of the most exciting day of my life is we see the PX actually spinning with the CO2 inside. And we started, of course, throughout the following weeks, we started changing the composition of the CO2, the operating conditions, and things like that. Then up to that point, we proved that PX can work in the environment, i.e. with a fluid medium, which is CO2. But we haven't proved that we can save energy for CO2 refrigeration. So from that point, all the way until 1 year later, we actually proved that. In fact, we try very deliberately before we jump into building a CO2 loop. We really want to know, what are we testing? Do we have a value proposition? Can we really save the Earth by reducing the carbon footprint? By how much energy we can save? That's the bottom line we have to understand. So initially, we worked with MIT, and they did a fundamental thermodynamic calculation for us. And that was a great project, Trevor. They proved that, yes, we can easily save what we think we can save. Is 30 to 40% easily under certain operating condition. So with that report, we really excited to present to our management, and our management was very excited about the news too. And so with our proof of concept, with both in the laboratory as well as the analysis with MIT, we showed that this is a device worth the human being to take a look at. And at the same time, we are the leader of pressure exchanger. So we decided that this is the time for us to invest. And we convinced the board. We are a public company. Yeah, you might not know, Trevor. We actually list in the NASDAQ since 2008. It's a public company, so we have to announce all the things we've been doing. And if you go take a look at the 10K, you'll see all these histories. We've been very, very diligently and methodologically trying to identify how can we actually contribute? Can we really contribute? How much we can contribute? Does it make sense for us to contribute? I think we answer all of the questions above with a positive answer.
You know what I'm so excited about is that you guys started off trying to help the environment, and now your device is going to participate in another massive change in the industry, which has happened right now, to help once again that the environment, what is going on this planet. And that's when I first heard about it. I thought that was really cool, hearing that history of it, that you're trying to help make fresh water, because we know there's only so much fresh water on this planet. As we continue to consume it, we need devices just like that. And it was crazy just to hear that story of where it came from to where it is now. And now we're in the CO2 world, in this realm, which I am stoked to hear more about and learn about, because this is my playground. And I love hearing about these technologies. So when you figured it out, so we talked about it, you started out, you learned about it, and there's a lot of naysayers, which I love that you said that. You get someone is saying they're naysayers, and then all of a sudden, let's prove them wrong. I love that, because that's the way it goes with a lot of things, and you're proving them wrong. And you're going to continue to prove them wrong with the things that I've heard about this device. So you spent a year, you worked with MIT, you did all these testing. What is it? How many installations do you have now? Do you have any installations in the field? I'd love to know that, because I know the desalination side, the reverse osmosis, you have thousands of applications or thousands of products out there. Is that right?
Yes, Trevor, thank you for bringing back to this topic. You're absolutely right. The reason why we have the confidence that we can actually contribute is because not only because of our current device, the PX G1300, but also our track record. because this company has been here for 25 years, and we are the inventor of this device called a pressure exchanger. And up to now, we deploy more than 30,000 of this PX around the world. And the majority of them, of course, as I mentioned to you, is all for water treatment purposes, either desalination or wastewater treatments or other water-related industry. As long as there's a pressure letdown, the pressure actually got wasted. And you can see our devices over there try to save the energy for the customer, for the local people. And so since then we have always been the market leader, because the PX is an extremely simple device. It only got really the main part is only 4 parts, and with only 1 moving parts. So it's extremely reliable device, because you hardly have anything to fail. So in the desal industry, for example, it is a device, as you point out rightly, water is very essential to our human life. And at the same time, we have a lot of places in the world is short of water. So that's where the desal actually contribute to the mankind. And originally, the reverse osmosis, which was the latest greatest technology to come up with to convert the seawater into fresh water, drinkable water. But it has originally about 20 years ago, has one technical hurdle, is the pressure required to push the seawater through the membrane is so high. And so you require a lot of energy input. But at the same time, after you push them through the membrane and you got the fresh water on one side, then you got the salty water on the other. So that salty water, you still got a high pressure. The high pressure, then you just dump it. Once you dump it, you lost that energy forever. So that's where the PS comes in and try to save the energy. From this kind of setup for a typical water treatment plant, we can save about 60% of the energy. And that's being well documented in many cases. Then let me move forward to your second part of your question. And you're absolutely right. We are relatively new to the CO2. But with all this track record, we know PX is extremely reliable and extremely high efficient and in terms of converting the energy. Recover the energy. So we believe that we can easily contribute to the CO2 refrigeration. So we started to actually deploy several PX. First of all, in the US, in a supermarket called the Vallarta. A Vallarta supermarket is a California chain, and they have over 50 stores over here, and they are still expanding. It is a supermarket very conscious about the environments. They're really looking into not only looking into the scope 1 GWP. They're looking into the scope 2 savings and scope 3. So in terms of scope 2, one of the key things they try to accomplish to their scope 2 target is try to reduce the refrigeration power consumption. Because as we all know, and you know better than I do, Trevor, I'm still a student of refrigeration. I'm learning too myself. And I learned it amazingly that we find out that there's so much energy was used for refrigeration, right? But in the meantime, I have to say it this way, is there are also a lot of energy which actually can be recovered so that the refrigeration, the energy required for the refrigeration can be reduced. And essentially, I'm a mechanical engineer. I truly believe that the way to actually make the earth green again is really try to save as much energy as possible. First, we prove that we can do that in the desal business, because the desal business, for example, the reverse osmosis was almost going to die until PX actually show up. Then we helped the adoption of the reverse osmosis in the water business 20 years ago. And right now, I'm very proud to say that the reverse osmosis in desalination is the mainstream, is every single new desalination plant you build on the earth right now, as we speak, they all use reverse osmosis. And every large project using reverse osmosis all have the size, the beautiful energy recovery size in their plants. So we, literally speaking, to some degree, I understand that we need to be humble, but it is also a fact that we revolutionize this water business, the water industry. If we don't do this, actually, they're still using the cooking. They actually provide the thermal energy to cook the salty water. and actually generate the fresh water, distill the water. That will be very, very, very expensive, right? Then with the same token, same analogy, that's what we hope we can do, i.e. we can basically reduce the power consumption, the energy consumption of the CO2 refrigeration, so that people can easily think that, hey, you know what, this is the right solution, okay? This is actually lower cost. Not only is it good for the planet, it's good for my purse. That's exactly what we want to do, so that we can helping people to make the right decision. Right with note that this is the right decision to go with the natural refrigerant, go with CO2, because there is some, well, again, you know better than I do, Trevor, there is some perception that under high temperature, the power consumption of CO2 is very, very high. In certain degree, it is true, but with the PX, we can help. So that's basically what we're doing. So we have several installation in the, we have first installation in Vallarta, and recently we present a showcase. That's where you and I met in Edmo, America, in Washington, D.C. just 2 weeks ago. And we presented the showcase over there. And so the data we got right now, when we first went in about last year, and we see about 19% of the saving, okay, when you switch on and off of the PX during the winter time, which is the November 1st when we went in. Then after that, we've been having there is an independent third party and doing the measurement and validation and following the industrial standard IPMVP. Then so far, the data we got in the last month is the main data, which is I presented in the Edmo America. We show 30% of the saving. So that was one of the installations we have, and we're very, very excited about that. So what we do over there is we turn on the PX every 2.5 hours, and we turn it off purposely. Well, the MV company do that. Then we basically is collecting the data like this way. Then of course we have a full-blown program. We intended to collect data the whole year. And so far, I apologize, I only have some of the partial data. One data point is in the winter, we save 19%. Then the other data point is we're able to save 30%. And in the summer, well, it is summer now. In May, in Southern California, it is summer. So Trevor, one thing I do want to bring to your attention, you probably remember, but the audience over here might not know, is this particular setup in Indio, California, is in the Vallarta supermarket. They use a CO2. They try to be compliant, but they see the high power consumption. But even with the adiabatic cooler, so they do actually have an adiabatic cooler over there, and they have water consumption. They have power consumption over there. And even with the adiabatic cooler, we all know that adiabatic cooler does help the CO2 energy consumption. But even with that, we did not turn it off. We basically just turn on the PX and turn it off. Then even with the adiabatic cooler is already saving, we can save extra 19% or 30% on top of it. And so one of the things we plan to do is, as long as we do it in the legal framework, then at the same time do it in a very, very safety manner, then we like to actually turn off the adiabatic cooler and showing that we can actually save even more than 30% in summer. Which we believe we can do it. But right now, of course, we are planning to do that. And once I have the data, I'll be happy to share with you and also the audience over here.
That's so exciting. Like, I'm excited about this because this sounds so great. Because when you explain how it works, which we're going to go through very shortly to the audience, it was kind of, for me, it was like, wow, this here replacing compressors removing compressors from the system. You know, and the easiest way to, save energy is to shut off your equipment and you don't have any refrigeration. That's easy,
right.
But then you can't sell anything. And like you said earlier, refrigeration is the most expensive part of a supermarket or a cold store. It's the most expensive part because it uses the most amount of energy, like you said. So anywhere that you can reduce that energy cost, that's a huge bottom line lift for that end user. Because we all know that they have to sell a lot of groceries. A lot of people think, oh, grocery stores make huge margin. No, they have to sell, their margins are real small. They have to sell a lot of grocery bags. People got to carry a lot of bags of groceries out of the grocery store for that store to make money. So now if you can reduce that bottom line, that actual cost coming out of their pocket, this is huge, huge.
Thank you, Trevor. Yeah, you're absolutely right. I'm sorry, go ahead.
No, you do.
Yeah, you're absolutely right. So we're very, very excited about all the savings we see so far. And I think the most important part is if I can just briefly talk about how PX work. And then I think that was your question. And I in the Atmo presentation, I did talk about that very, very briefly. But over here is I would like to actually give you and your audience. And by the way, Trevor, you did an excellent job explaining how the PX work. And I think that the audience can always refer back to the video you took 2 weeks ago. I think you did a fantastic job. So let me take the risk and try to explain that again. and let me know if there's anything actually is not very, very clear to you. I have to say that PX is an extremely simple device. You only have 4 ceramic parts, 4 main parts. But at the same time, it's an extremely complicated device. Because in order to make it very, very simple, we also have to really, really understand how the things work. So in essence, and you're absolutely right, the reason why we can save the electricity is because PX can replace some of the compression required. And at the same time, the PX provide the compression for free. And the energy the energy we recovered is coming from the pressure letdown, from the gas cooler going through the HPV, then the pressure just basically let down. Then once you let the pressure down, then you lost this energy forever. So PX to a certain degree is doing 2 functions in a single device. On one side, you can think that it was actually performing like HPV, like a pressure valves. Then the PX have one moving part, which is actually a rotor. The rotor, you spinning faster, then you have a more flow to go through. That means you're equivalent of opening up your valve, your HPV. If you started to slow down your PX, then in certain time, the flow you go through the PX is going down. Then you pretty much is behaving like you're closing up the valve. So in one way, there's only one control parameter. This control parameter is the RPM of the PX. The faster you run, kind of like you open up the valve, HPV. So you're dumping more CO2 from the high pressure gas cooler into your receiver. That's it. Okay, very simple. But at the same time, why you are actually doing, now you say, okay, why not we just go with HPV? Of course, when you do HPV, all those pressure laid down, the pressure energy is wasted. Then you generate actually entropy and dump it into the universe, and you cannot recover anymore until the end of the universe. So now what we do is when the pressure was actually letting down inside the PX, we actually induce that pressure and we go through what we call the pressure exchange process. And that pressure exchange process can recover that energy. That pressure will not be wasted because we use that pressure and to compress the low pressure CO2 and make that into high pressure. So in a sense that the high pressure from the gas cooler become low pressure, but the low pressure gas, for example, from the evaporator can get compressed into high pressure. So the PX is acting like a compressor, but the most important part is it does not require any electricity. So every time when I reach to this point here, Trevor, people are saying, Casey, come on, that's too good to be true. This is not the first time I heard about this one. They are at least half dozen of people just basically with a straight face and say, Casey, I don't believe that. That's too good to be true. There's no way you can do it. No way you can do it. But in reality, that's exactly how we did it in the water business. Okay, so let me kind of briefly explain how you work. How you work is, let me draw an analogy. By the way, a lot of people say, this is just a heat exchanger. These people are not wrong. Basically is in the heat exchanger, as you can see, you have a one hot pipe, okay, with a hot water or hot CO2, doesn't matter, okay, from the gas cooler, for example. Then you have a cold pipe. Then the only thing you have to do is put a hot pipe and cold pipe together, then your thermal energy will flow from the hot to cold. As we all know, that's called a heat exchanger, right? So you guys are all the expert, including your audience. Everybody's an expert here. I don't have to explain how the heat exchanger work. Pressure exchanger is almost the same, but you have to do it dynamically because you cannot just have one high pressure, one low pressure, put them together in a pipe, hoping that they will transfer the pressure. No, it will never work. So the way you're going to do it is you have to open it up very briefly. When the moment you open the high pressure, expose them to the low pressure, there will be a shock wave going through this duct. And this duct can transfer the pressure from high pressure to low pressure. So suddenly your high pressure from gas cooler can transfer to your low pressure from your evaporator. So high pressure become low pressure become high pressure. Kind of like an analogy of the heat exchanger from high temperature to low temperature, but low temperature to high temperature. Yes, but in this case, only difference is this is not a thermal energy, this is pressure energy. And the way you do it is not statically using a hot pipe. Well, of course, the fluid is dynamic, but your pipe, two pipes, is static, right? They touch each other. That's how you do the thermal heat exchange. But in a PX, you have to do it dynamically. This is where all the trick is coming from. You have to making sure that you open up the pipe briefly, then close it. Open, close, open, close. In a very, very managed way, so that your pressure can always transfer from high pressure to low pressure, high pressure to low pressure, and do it continuously. Okay. So now, of course, you guys probably getting tired of my hands. let me show you the real thing. Okay.
Awesome.
So can you see this device over here?
Yeah.
Let me take it off. And so as I mentioned to you, we only have 4 ceramic parts. This white piece, actually we cut in half, is really real ceramic parts. Okay. And this is fairly heavy and very, very sturdy. And that is the reason why the PX, even though there's a debris going through, is not going to damage it. And we're already proving that in the water business. And majority of the PX we deployed 25 years ago, still turning. So that actually make our aftermarket sales not very good, but that's okay. We're saving the earth. It's all worth it. Okay. So once we take this off, as you can see, then you have one sleeve. I don't know whether you can see clearly, but you do have a ceramic sleeve. And inside your sleeve, you have a rotor. And inside these rotors, you have a bunch of ducts. Okay. And this rotor will keep rotating. And the RPM range from about 100 RPM all the way to 1600 RPM. Okay. So you got a very, very wide range of operating conditions. That is the reason why for majority of the supermarket in the US and Europe, you just need one PX for your refrigeration system. You don't need multiple a compressor, multiple ejectors, multiple this and multiple that. No, one. Okay. The reason why you only need one is because we can control the RPM. The faster it runs, as I mentioned earlier, then you can have a more flow go through. The slower it runs, you have less flow go through. Okay. Now, every single hole you see over here on the rotor, while it's running, is actually a straight ducts. Nothing but straight ducts. And then your high pressure comes in over here on one end. Then your low pressure comes in from the other end. And when the ducts align with the housing hole, the holes on the housing, that's where your ducts is open to the high pressure, or your ducts open to the low pressure. When they open it up, they're actually, this flow will comes in the middle of the duct. Then they will actually meet each other, right? That's where the pressure shock wave will actually transfer the pressure. So then at the same time, while it's transfer the pressure, then you'll keep rotating to the next one. Then the high pressure become low pressure and get dumped into receiver. Low pressure become high pressure and bring it back to the intake of the gas cooler. Okay. So if you keep doing this one while the duct is rotating, as you can see, you almost do it continuously. So your pressure shock wave is actually keep doing it this number. So you keep transferring your high pressure to low pressure. And low pressure become high pressure become low pressure. Just like your heat exchanger, but in this way, you do it dynamically. Then the more important part is that all the things are ceramic. And unlike your compressor, you will have seals, you'll have the pistons, you'll have piston rings, you have actually bearings, you have all those mechanical devices. It's all known to fail. I don't care how people say it, as long as it's a mechanical device, it's going to fail one day, including PX. However, the PX, we don't have a mechanical seal, we don't have a mechanical bearing. Everything was done by fluids. First of all, you don't have a piston, you have a fluid piston, because you have actually the high pressure fluid comes in, meet with the low pressure fluid, and the time scale is so small, it's actually speed out sound. of the fluids, right? So the time scale is so small, you only need this pop. Once you pop it, low pressure becomes high pressure becomes low pressure because the shock will propagate, right? Once it propagate, okay, then you actually go to the next state, next position. Then you actually should seal this whole thing off. While you're doing that, you don't give it enough time for this high pressure and low pressure CO2 to mix. Because, for example, in the water business, you have a salty water, you have fresh water. You want to transfer your fresh water, salty water to fresh water pressure. You don't want to mix it. The mixing in this device is less than 1%. However, the pressure transfer is 98.5%. So extremely high efficient to transfer the pressure, but it's extremely low time scale for the species to mix. So you don't worry about the species mixing. That's exactly your idea. So to a certain degree, you still have two pipes, okay? But this time, you're not transferring temperature, you're transferring pressure. You just open it up very quickly, very quickly. That's so quick to the point that you can transfer pressure, but not transfer the species, okay? So in that case, we don't have a valve. We don't have a piston. Everything is done by fluids. And you know what? You can make fluid fail, granted, because it's still a mechanical device, but it's very difficult. You don't have a valve like open, like close like this way. They just basically like it's a duct, open, close, open, close, open, close. Okay, that's one. Number two, you don't have bearings. All these rotors you can see, which I'm rotating with my hand right now. Okay, this is actually a real PX. We cut in half so that we can show it on the training courses. Okay, how the PX actually work. Because this is a very, very simple device, but its concept is not very intuitive. Because what happens, the heat exchanger is very, very intuitive concept. We all know that the heat flow from high temperature to low temperature. But we also know that the pressure will flow from high pressure to low pressure, but you need to give it the conduit. So all the things it's doing is providing that conduit in a very, very reliable fashion. So you will think that this is a rotating device, so you got to have some kind of bearing, right? But no, it actually does not have a bearing because the machining of this ceramic rotor and sleeve are so tight. They're actually in the micron level, actually thinner. The gap is thinner than my hair. Then my hair is actually very, very thin. but what happened is actually is 1/10 of the size of the hair. But even I use my hand, I can rotate it. As you can see, what kind of machining we have. It's very precise machining. But this tiny little gap will fill with CO2, which is actually acting like a lubricant. And also is a thin film, right? And this thin film of fluid, if your rotor is running fast enough, it's kind of like you're driving on the highway while it's raining. Now, certainly we all know that there's something called a hydroplaning. That was exactly the bearing we have. It's hydroplaning. It's a hydrostatic bearing. Is your rotor is rotating so fast inside a very, very precise control gap. And that gap actually providing a thin film now have high enough pressure to lift everything up so that this rotor will floating inside this sleeve, never touching. And then Trevor, as we all know, when there is nothing touching, there's nothing to fail. How can it fail? That's the reason why this PX can rotating for the water desal, and also in the future will prove 25 years later, you have to take my word for it, is in the water business, it's been rotating for 25 years. Most of them is still going. Most of them is still going. And then the other thing is, it also does not have seal because the gap is so small, right? So you will have some leakage. Again, the leakage is less than 0.5%. Very, very tiny little leakage. So you don't even need a seal. You just let it leak very, very briefly. But so you lost a little bit efficiency. That's the reason why this is not a 100% efficiency. It's 98.5% for a good reason. If it 100% is a perpetual machine, then I'm going to win the Nobel Prize. But we know that that's not a perpetual machine. We're working on it, but 98.5 is as good as it gets.
So this device, all it needs is actually, I guess, a motor on it, like a smaller motor to spin it, or how does that work? Is there other devices that you need? Because this device looks pretty simple. It's a straight in and out from high pressure to low pressure. But is there any other devices that you would need to make this work?
Yes, Trevor, that's a good question. In fact, what we did not show over here is at the end of this this rotor, we have a shaft, and that shaft connected to AC motor. It's nothing but all of the offshore AC motor, and that AC motor. The reason why we need that AC motor is we basically sometimes we use that to actually accelerate the speed of the rotor. Sometimes we actually slow down the speed of the rotor because the rotor, the fluid flows will prepare the PX itself. In fact, in the water PX, we don't have motor. The water PX, you only need to actually make sure that the way your flow run into your PX is tilted a little bit so that it generates enough momentum to rotate your rotor automatically. And in the water business, the operating condition is very simple compared to the supermarket or cold storage, because nobody's going to go over that to open up a tap and close the tap, and so that you change the volume flow rate of the water. No, the volume flow rate, the RPM, everything operating condition is fixed 24/7. But in the supermarket, it's a little bit complicated. As we all know, the ambient temperature go up and down, so that changes the gas cooler pressure. When you change the gas cooler pressure, as we mentioned, part of this PX is acting like a pressure HPV, a pressure control valve, right? Now, part of this PX, the other half of the PX is acting like a compressor, which is also affected by the how much it actually get the vapors you have, how much gas you need to compress. By the way, there's one more advantage of PX is, to a certain degree, we don't care about superheat, because we all know that the reason why you care about superheat is because you are like to making sure that your compressor is not going to see liquid. But as I mentioned to you, this is a true multi-phase device. We don't care whether it is, in fact, you're actually constantly having supercritical gas and liquid inside. Sometimes even inside in a single duct, have a multiple phase. It's not going to destroy it. There will be shock wave, okay, but it's ceramic, so we are not going to have a cavitation. It's all fine-tuned to the point that it's not going to fail. So, with that being said, so this device is extremely reliable. At the same time, when we do this this rotation, the motor we need is really try to just control the RPM, and this RPM actually depends on how you use it. Because as I mentioned to you, if you're rotating faster, it's kind of like open up the valve. When you open up the valve, then if you actually put this one downstream of your gas cooler, then it is equivalent to your HPV is open. So your gas cooler pressure will go down. So if you actually slow down the rotation, your gas cooler pressure will go up. And there is a pressure curve. Actually, we optimize the performance of the whole system, not just optimize of the PX performance. No, it's optimize the whole system performance. Depends on the architecture you have, right? So with that being said, motor really is the one extra items we need, okay? And the control is very straightforward. We just control the RPM. That's it. So what you see over here is you have a 4 ceramic parts, then you have a pressure housing, okay? Then which is UL qualified and CE qualified. Then also it can be used in Canada. Then what you need at the end is the AC motor, which is off the shelf, couple $100 AC motor. Majority of the time is actually acting like a brake instead of actually providing energy. Sometimes you require a little bit electricity, like less than 0.1, 0.2 kilowatts to accelerate. Because now let's say that the outside temperature is very hot, then you have a lot of hot gas. You actually have to dump it. Then in that case, you want to open up your HPV. So equivalently, you want to rotate your PX faster so that there's more flow rate go through. Then that's it. That's the only thing extra.
Wow. Because that's something important in CO2 is where we would need, depending on the application, you may need to increase that pressure for heat reclaim, heat recovery, for an example. So I'm excited to see a lot more of this. So can you give a picture of what pipes, because I know one, you said you're coming from the gas cooler down into the flash tank receiver. Where would the other 2 pipes on the low pressure side be coming from?
Right. So one of the architecture of the refrigeration system, which actually is kind of like an intuitive one, is you basically take low pressure from the output of the evaporator, or you can actually take the intermediate pressure from the vapor of the gas cooler, then you want to put this at low pressure and compress it up to high pressure by replacing the compression required by the empty compressor or parallel compressor. So in this case, you really don't need a parallel compressor anymore, because let's say that you have fresh gas bypass. Used to be you dump your fresh gas through your fresh gas bypass valve, right? Then so that you compress it by the empty. But later on, people introduced a parallel compressor, which is very, very smart. Then now you don't have to dump it and compress it. Okay, you just compress it from the intermediate pressure, the receiver pressure, to the high pressure. That's another way to do it. But with this one, you can try to imagine that you just replace your parallel compressor directly with PX. The only thing is your parallel compressor requires electricity. This one does not require electricity. So that's one way to use it. Okay, so is now your PX is acting like HPV on one side. On the other side is like your parallel compressor. So HPV, that means your high pressure input is from the gas cooler output. Then your low pressure output goes to the receiver, right? Then your input can be from the let's say fresh gas bypass, and or from the evaporator. Either way is low pressure. Then you can go through the low pressure in of the PX. Then the high pressure out of PX can go directly to the gas cooler input. So you replace the parallel compressor, but you don't actually use any electricity. That's one way to use it. There are other ways to use it, Trevor, and we are working with different OEMs and develop different architectures. And some of the architectures, it is trying to addressing, for example, is subcooler. So you can try to imagine that your subcooling, right? You try to generating more liquid instead of fresh gas by introducing little mini subcoolers over there, right? So that subcooler also actually is acting like refrigeration itself. It's a small circuitry, which actually is cooling your fresh gas output from your gas cooler. So with that subcooling, you have more liquids in your receiver. That makes perfect sense, right? And we all know that subcooling is how you work. But one thing is, you also have a catch. You need to actually move that output, the receiver from the subcooler, and put it back into the whole system. That also requires compression. That compression can be, again, replaced by PX. Again, this is a compressor which does not require any electricity, right? So that's another way to use it. There are many, many other ways to use it. But fundamentally, Trevor, you can try to think this way. As long as you have a high pressure, your pressure let down, okay, which is energy wasted, we can recover. As long as you have a pressure like that, then you have a low pressure you want to compress. You always, because we all know that refrigeration is a cycle. You have to compress the low pressure to high pressure, or intermediate pressure to high pressure, or medium pressure to high pressure, whatever you want to do. Or maybe even from low pressure to intermediate pressure, right? I'm trying to give you a hint. Then, as long as you have a pressure let down, then you actually have a pressure you want to increase. PX can actually fill in the gap. Instead of using a compressor, you can use the PX. The only thing is, you buy the PX, from that point, you don't need the electricity, you don't need the water, you don't need the maintenance, you don't need anything.
That's game changing. I love hearing that. So from just our conversation right now, your target market, I would be assuming, is supermarket. Have you ventured off into other areas like industrial yet, or you're focusing on the supermarket arena?
Yes, Trevor, you're absolutely right. Actually, we got encouraged by some of our customers and saying that we should try industrial. In fact, some of our customers even tell us that we should start from some of the light industrial or industrial applications. We have one installation coming up in Europe, and in fact, it's in the planning stage, and we're going to go in fairly soon, in the coming months. Is a factory, is a food processing factory, and it's about 1.2 megawatts. And we're trying to, and in that case, it requires more than one PX. Okay, so the PX is this PX is this particular size. I would love to say one size fits all, but it's not quite. It can cover about from 20 to 40 kilowatts in the low end, all the way up to about 200 kilowatts in the high end. So if you have some some application which require more than 200 kilowatts, what we can do is we can put it in parallel. So that equivalently you double the flow you can handle by putting 2 in parallel. Then you triple by putting 3, quadruple by putting 4. It's very, very linear. So for example, in this particular food processing factory, the customer is planning to put 4 to 6 PX into the existing rack. And we believe that that will work very, very nicely. And the architecture is very close to what we just described, okay? And it's basically is the parallel compression architecture, okay? That's one of the architecture. We plan to do that in the first. There are also subcooling architecture we believe is also doable. And at the same time, Trevor, just let you know that you're absolutely right. You mentioned heat reclaim early on. And because we can control the RPM, which actually can changing the pressure profile, not only the input, but also the output, okay? So even though we say we just control RPM, but in reality, we are controlling the pressure and temperature by changing the RPM so that the heat reclaim can still work. In fact, we have one installation in Belgium, which is a supermarket using heat reclaim. So both the heat reclaim and the PX is helping the supermarket to save money, which I think is fantastic.
Yeah, no, I totally think so too. Another question would be, is this better to be put on a new installation? Can I actually take this and add it to a site right now? Like, do I need to pull out the high pressure valve? Can I leave it in? Like, what's the options?
Right. So Trevor, of course, PS can use on both of the situation, what we call either the green field or brown field. The green field, let's say that you basically put a PX into your rack from the very, very beginning on day one, then you ship the whole rack into your site, your supermarket or your cold storage. And in that case, one of the advantage is not only just OPEX saving anymore, you also have what we call the CapEx offset, because now you have compression capacity from the PX. You don't need to have as many compressor as you originally designed for that extreme temperature, right? We all know that when you design it for supermarket, you need to design it not for just 20 degrees C. You need to design it for 30 or 35 or even 40 nowadays, because the temperatures keep going up. There are more and more heat waves as being reported. So in that case, you probably can put a PX in, not probably, you can put a PX in a greenfield installation so that it comes in by replacing the compressor. That's how we call the CapEx, capital expenditure reduction, the offset, right? So of course, you can also use on what we call the brownfield, i.e., for example, like this Belgian application in the supermarket, and we were talking about the heat reclaim just now. That one already have the rack, and already have a heat reclaim. Everything is already up and running, but the store owner really want to have an extra saving. He asks us whether it's doable. After our analysis, we believe it's not only doable, we can save a lot. So we actually go in and with 2 PX in this particular case. It's not quite an industrial application, but this is the first one we actually put 2 PX side by side in parallel. And in the desal business, we're doing that almost by default, because the desal plant is very, very large. And you're talking about huge gallon per minute of flow rate, right? Huge amount. So then you don't want to build your PX too big, because in terms of transportation, there's all kind of issue. So we put PX in parallel. For a typical application, you have a 40 PX in parallel. Sometimes you have 100, 200 PX in parallel. That's being done all the time. So now in this particular supermarket, it's about 300 kilowatt. So we put 2 to making sure that during the summer, there's plenty of compression capacity can be replaced by PX. Then those 2 is working right now, okay? And sometimes you can actually shut one off, just let one do all the job. Sometimes you can actually have both of them so that you can handle more fresh gas. So so the answer is yes. Yeah, you can absolutely you can absolutely do that. You can absolutely do that.
Yeah, no, that's amazing, because the way you can structure this, because there's not only one option. that's what I like about it. You can put it in multiple places as long as you
Mhm.
have a high pressure input to it. Um,
Right.
so,
It
so
can be
this
used.
is
Yeah, I'm sorry. Go ahead.
this is exciting to hear because this is what end users, even manufacturers, even how do we reduce the cost for the end user? And when you can remove the amount of compressors needed, that because that's the biggest cost running
Right.
so many compressors. And this is a technology I think that is going to continue to grow. And I like that it's in the early stages because I really believe after this, as more people start to know about it, there's going to be more field installations. And this is because I've seen this working for a manufacturer. Even though something's proven, everybody went, "Oh, well, we need to test it. We need to test it." You've been testing it for 25 years in the water industry already, so there's a lot of testing behind it, which is great to hear. I'd love to see some different applications at some point, and I know we're going to see it. I know we're going to see it. And what I mean by that is that having the heat recovery, which you already said that you have, and heat reclaim, as well as I'd love to see it in the applications where it's really cold. Like here in Canada, we get real cold winters. So how does it perform in a cold winter? You won't have as much flash gas, so you won't need to be using it as that much. So how do we move that? And is there other ways to save in cold climates using this PX device? Because now I had a few conversations with people with different technologies and what they're trying to do, and especially with CO2, is like how do we
Mhm.
move refrigerant without having to use compressors? And this is one way of doing it. I'm super excited about this.
Right, Trevor, that's an excellent point. Thank you very much for bringing it up, because we do have an installation coming up in a colder climate in North America. You can guess it's probably more likely in Canada, but I didn't say it. It's coming. So we intended to prove two things. The first thing is even in the colder climate, in the colder weather, colder season, you can still save. You might not save 30%, but you can still save, as I reported early on, in India, in the winter, you can save about 19%. But as we all know that Southern California is pretty warm, now is Canada, right? And we have some theoretical numbers calculated, and we also run it in the laboratory. But what we really want to see is we can save the money for the operator. And we intended to show that even during the winter, even during when there's not a whole lot of fresh gas, but what we really trying to do is we shut down the compression by compressor. But using whatever the fresh gas you have, whatever the pressure let down, energy, you're going to waste it, but we recover it. Number one. Number two, Trevor, is for doesn't matter is a greenfield or brownfield application. We believe that we can help the operator's CO2 system become future safe, because we all know that the heat wave is getting worse. The whole global warming is making the climates going a little bit extreme now. Then there are more and more heat wave reporting, and unless we all want to go back to the caveman era, we all shut down the refrigeration and AC and stuff like that. We need to have a refrigeration. We need to keep the food fresh. But the thing is, can we do that efficiently so that we don't have to burn as much hydrocarbon or electricity as possible, so that our temperature will not keep going? That is what we feel is part of our mission. And but for the time being, because the heat waves just keep popping up, one of the value proposition we believe is we can, even especially for the brownfield, we all know that for typical supermarket, you go in and you design for the extreme temperature and plus another 15% or maybe 20% of capacity, just in case for that raining day or for the hot day, really, for that hot day. And with PX, we can actually provide that. The PX, as I mentioned to you, it is actually an extra compressor. Okay, so you don't need to put it into the extra capacity in the PX, in the compressor. You can put PX in. And during the hot day, especially during the heat wave, there will be plenty of fresh gas you have to handle. So PX will not worry about this, not enough fresh gas, even in the northern part of the Earth, because you still maybe just have 1 or 2 days of the heat wave. But during those 1 or 2 days of heat wave, we're constantly hearing people reporting that they have to shut down the supermarket or they have to do the ice cream sales. In fact, Trevor, while you and I were in Atmel America two weeks ago, one of my colleagues actually sent me a text message and say, hey, they just actually have ice cream sales in my neighborhood because my colleagues actually live in Vancouver. And they said they just have an ice cream sale because there's a heat wave. Because they have to actually start to get rid of the ice cream so that to save electricity. But the PX can provide an extra capacity, cooling capacities, and especially during the heat wave. So the heat wave, of course, people tended to maybe tended to actually underestimate the requirement. But at the same time, you basically build the extra capacity for nothing. Majority of the time, you're not using it. But PX is one fits all. In a cold weather, it will help you to save electricity. Maybe not as 30%, but some. But during the extreme hot day, it provides you the extra capacity, which you can safely see through the heat wave. So this is basically what we think we can contribute throughout the year in the north.
Yeah, no, I'm excited to see more of it, and because these technologies, they'll evolve, which I've been seeing with tons of CO2 technologies. They start in one place and they continue to grow and expand in other parts of the refrigeration industry, from refrigeration to heat pumps, and we're going to see lots of it. I'm super excited to learn more about this. We do have a couple of questions. I think you answered already. Is there CRN on it so you can install them in Canada? I know there's a ULC maybe you have on it.
Mm-hmm. Yeah.
Okay.
And it's ready to go in Europe, in the US, and also in Canada.
Awesome. And then I have a question. So I think you might have mentioned there is only one size design, and that can go from 20 to 200 kilowatts. Is that correct?
Yeah, about 2040 to 200 kilowatts. Yes.
Okay, 20 to 40 to 200. Because I have a question. How can we estimate the pressure reduction? Do you need to calculate the pressure reduction? I'm assuming you will. So how would you calculate the pressure reduction? And I'm assuming the question is towards, because you have to have a stable splash tank pressure of whatever temperature you want to supply. How can you calculate that?
Yes. So the flush tank pressure still be controlled by the valve downstream, just like the regular system. So that one, we basically is just accommodating that. The PX is not a driver here. What PX's driver is the gas cooler pressure. Yeah, which actually will be controlled by PX. The faster we're turning, then you are dropping pressure. The slower the PX is turning, you're kind of closing the valve because now the flow rate goes down. So your pressure starts building up. So the gas cooler pressure goes up.
Excellent. And I don't know if you're at this point yet, but was the PX performance compared to other pressure exchangers, for example, like ejectors or thermal driven pumps yet?
Yes, yeah, we haven't do a experimental direct or a supermarket direct shoot off. We haven't done that, so it's difficult for us to claim.
Yep.
But one thing I do want people to think is this is actually a pressure exchanger. That means that you actually change the pressure. It's not a mixer. A lot of devices, they are actually mixer.
Yeah.
I.e., you mix the high pressure with the low pressure and become the intermediate pressure. So the mixing, by definition, as I mentioned, it destroys enthalpy, which actually, by definition, you have a lower efficiency. So this one is 98.5% energy recovery efficiency. So I think there are literature out there about the energy recovery efficiency of other devices. We can do a literature comparison directly.
Yeah, no, I have so much to learn. I do have so many more questions because just understanding the science behind it, I love that. It makes me curious of what's going on. I'd loved everything about this conversation. Casey, how can people get a hold of you, get a hold of your organization, best reach out to you to find out more about this product?
Yeah, please check out our website, energyrecovery.com, and they are a way to actually communicate with us. We'd be happy to actually get back with you with any questions you might have, things like how does device work, and whether it's actually you have a system you can implement it tomorrow. We'll be happy to help. We'll be happy to help.
I love that. I love that. So I want to thank everyone for taking the time to hang out with us here on World Refrigeration Day. If you enjoyed this, please share it with someone. Please share this technology. because there's more people looking for other solutions, and this could be the option for your customer. So I'm super happy that you were able to take the time, Casey, today. I want to thank everyone for spending the time with us, learn a little bit about the PX G1300. I really appreciate your time, and I'll see everyone at the next CO2 Monday. Thanks, everyone.
Thank you, Trevor. Thank you, everybody.